So we're very happy to have our friend Cody Long, who's going to tell us about statistical predictions and generative models.
Okay, thanks very much, Yang. It's a pleasure to be here. I want to start out by thanking the organizers for putting together such a nice meeting and inviting me to speak. So it's an absolute pleasure. So as Yang said, I'm going to tell you a little bit about statistical predictions and string theory and the way that we're trying to make them using deep generative models. This is work with Jim Halverson, who spoke yesterday, which appeared some time ago. So let's see if I can scroll. Okay, so before I dig in too deep, I want to just give a lightning overview of what I'm going to tell you about. So this talk is a modeling talk. So I have some data that I want to model, namely the metric on moduli space for certain algebraic varieties, namely Calabi-Yau threefolds. And I want to come up with some statistical model for these metrics. They can be represented as symmetric matrices, being metrics. And so at its core, what I'm after is a random matrix model with correlated entries drawn from some appropriate distribution, which is what we're going to want to figure out. There's a lot that we want to explore with these random matrix models, but one in particular, one of the most important things is how the behavior scales with the size of the matrix N, which is going to correspond to the dimension of the moduli space that we want to study. And there's many motivations for studying this metric that come from string theory. So the data, as I'll get to in a bit, is not easily reproduced by some canonical random matrix model. If it were, I probably wouldn't be giving this talk. So the question that Jim and I wanted to ask is, can we use machine learning to derive a random matrix model in the form of some neural net? And the answer I want to motivate to you is yes. So the candidate tools that we thought of, there are many possible options, which I'll maybe mention a few, but the two that really worked well were reinforcement learning, and in particular, the one that worked the best was generative models. That's the one I'll focus on today. So there are many applications of random matrix theory for understanding machine learning, but this is an application where we're using machine learning to derive a random matrix theory. So let me motivate this to you from the physics point of view a bit. Fabian gave a really nice introduction yesterday to some of the stuff I'm going to say, so I can be rather quick. So our general goal is to understand the statistics of the solution space of string theory, which I think is interesting in itself mathematically, but it's especially important for understanding how our universe fits into string theory. But the challenge is the size and complexity of the solution set of string theory. The solution set is absolutely enormous and impossible to put on a computer directly unless you're incredibly clever. I'll give you some numbers very soon. And the majority of the solutions are very complex and difficult and time-consuming to construct, especially when the number of fields becomes large. So a string vacuum, one of the solutions to the equations of motion of string theory that we want to understand, is obtained from, at least in 4 dimensions, from compactifying one of a few unique higher dimensional theories, which are either in 10 or 11 dimensions, on some compact space. So we take it, we wrap up some of the dimensions on a compact space and arrive at a 4D effective theory from the non-compact directions. So that space is going to play a major role in my talk today. And for the most part, I'm going to be talking about Calabi-Yau threefolds, which have 6 real dimensions. And I'll label this internal space as X. Now, we find light scalar fields arise from reducing fields in the higher dimensional theory on appropriate dimensional cycles in the internal space. And these light fields are counted by various Hodge numbers of X. And these light fields can have important physical consequences. There are good models for inflationary fields. They could be dark matter. They could help with producing dark energy. So a great deal of physics depends on these fields and depends on the geometric data of the internal space. So just to give you an idea of the size of this solution set, well, if I just restrict myself to a small corner of the string landscape that we know quite well, known as F theory type 2B, well, the number of possible geometries that we could compactify these theories on to get a 4D effective theory is bounded from below at about 10 to the 755, and is estimated to be as big as 10 to the 3000. In addition, there's additional discrete data that one can put on a geometry to actually arrive at an honest vacuum. And per geometry, this is estimated to be about 10 to 500 for a typical geometry and up to 10 to the 272,000 for some special geometries. So this solution set is absolutely enormous. The vacuum are all connected in a network of topological transitions, and each vacuum corresponds to a physical theory. So the point I want to make is the number of theories is absolutely enormous, impossible to enumerate, and is also increasingly difficult to study as the number of scalar fields, which I'll label as N, increases, where computational complexity takes over, as studied recently by Jim and Fabian. Okay, so since the solution set cannot be explicitly enumerated, we want to instead develop an appropriate statistical model to probe and make predictions. So in the theories that I'm going to be interested in, the data of the vacuum is specified by just some scalar function, which we call Lagrangian. So if we're just considering scalar fields, you write it something like this. You have a kinetic term, Kij, which hits the derivatives of the fields. You have a mass term, which is quadratic in the fields, a cubic term, etc., all the way up. So the theory is specified generally by, once you specify the field content, well, to write down the theory, to write down the physical data, one specifies constant tensors of various rank 2, rank 3, all the way up. So for a fixed number of fields, the distribution of theories is given by the distribution of tensors, I should say, for fixed field content. So in this sense, the statistical ensemble of these theories is just given by a random tensor model, where the entries just need to be drawn from the appropriate distribution and may exhibit very strong correlations. So the question that we want to ask is, how do we model this distribution? Can we model this distribution accurately? And can we understand the end dependence of the couplings? So let me, we're not quite to this stage of application, but let me give you just some motivation for what we might use these random matrix approximations, RMA, for. So for instance, we're interested in statistics of vacuum. What sort of physics might you observe? So at fixed number of fields, an accurate random matrix approximation would allow for understanding of what events are typical versus what events are rare, allow us to probe the probability of understanding certain physical features, which cannot be entirely enumerated in the ensemble. Also, sometimes the data is prohibitively expensive to obtain at very large N. So if we can obtain a random matrix approximation that scales with N, we might be able to probe the statistics of large N where we cannot reliably compute. I think it's also interesting that we might be able to reverse engineer. If we can come up with an accurate random matrix approximation, we might be able to reverse engineer it to learn something about geometry, as I'll make the connection more precise later. So the first step that we're going to study is looking at the metric on Kähler moduli space in type 2B and F theory. So let me just tell you what these fields are. They're very geometric objects. So if I take type 2B on an orientifold of, which is implicit of a Calabi-Yau threefold X, the Kähler moduli measure the size of divisors or holomorphic 4 cycles, codimensional 1 cycles in X. So these moduli T are, their values are just given by the volume of some divisor obtained by integrating the Kähler form twice, the Kähler form multiplied by itself over the divisor. And then they're complexified by this axion field. And we're going to be interested in the metric on the space. So the moduli space metric is given by 2 derivatives of some Kähler potential. The moduli space metric is Kähler itself. And the Kähler potential is given by -2 log V, where V is the volume of the internal space X, obtained by integrating the third power of the Kähler form over X. Okay, so this is just a review, probably for those who are already familiar with what the Kähler moduli are. But just more broadly, our goal is to learn a random matrix approximation for this particular metric, which is evaluated at fixed points in moduli space. So this is just a constant matrix. So at the end of the day, our data that we wish to reproduce is just an ensemble of real, symmetric, n by n positive definite matrices. And some time ago, we actually studied these metrics, not from a machine learning perspective, but just wanted to understand the statistics a little bit. And we found that the spectrum is heavy-tailed. So that's one of the features we're going to want to reproduce. And this heavy tail may have implications for a lot of physics, including vacuum stability, some experimental signatures for axion photon couplings, inflationary field ranges, et cetera. And as I mentioned before, this data does not seem to admit a canonical random matrix description. So how can we derive a random matrix approximation of these metrics? So we're going to try to learn a random matrix approximation and try to be able to extrapolate out of the training set and to large N. So what is a random matrix? How should we view these objects? So the way I want to describe a random matrix is that if I take some P random variables and I take P draws and I feed it through some machine, this is going to produce for me some random matrix, which in this case is symmetric positive definite. And a key point is that I can view this random matrix as an image where I color the smaller values of the real entries as darker spots and the larger values as lighter spots. So for example, if I'm talking about the Wishart ensemble, what I would do is, well, the number of random draws would be, if I have an n by n matrix, I would take n squared draws, I would put them in a matrix A, and then this machine F would tell me to take A times its transpose to get a positive definite Wishart matrix. So the question is, can we learn the appropriate F for our data from some sophisticated ansatz? Okay, so there's sort of two obvious approaches one might take in trying to come up with an F that produces the correct data. One is to search an ansatz space. So one is to use human cleverness to insert some structure in which has parameters and then try to optimize these parameters. Actually, the way we started out studying this was to use reinforcement learning for taking a Bergman approximation to this Kähler metric, where the Kähler potential is given by log of some polynomial f, where f is some sections of certain line bundles. I think Bergman metrics have already been discussed at this meeting. And then we were, these line bundles have coefficients, and we were using reinforcement learning to fit these coefficients to create a random matrix approximation to our data. And this worked fairly well. But what we found worked better was to take an approach where we learned the ansatz itself. So the other alternative way that we thought of was to use a very expressive form for F, this random matrix machine that can hit a lot of function space. And in our case, F is a deep neural network. And the training possibilities were, of course, just take a simple network and maybe train on decreasing the distance of the eigenspectra from the fake data to the real data. But really, the key thing that worked the best was using a generative adversarial network, which plays a competitive game until it hits an equilibrium and learns the ensemble. So I imagine most people here are fairly familiar with GAN, so I can go fairly quickly. So a generative adversarial network, or a GAN, it consists of two neural networks, G and D. So G is the generator, and it takes in some noise and fakes data from the noise. And its goal is to make the best fake data. The other neural net is the discriminator, which tries to discriminate between the real data and the fake data. And its goal is to discriminate really well. Its goal is to be able to tell very well if the data is fake or real. And so these two play off each other. The generator tries to get better at generating fake data. The discriminator tries to get better at detecting fake data. And they play a game until they hit an equilibrium, and then hopefully learn the data distribution itself. So of course you can, there are many different possibilities for the architecture. You can take the original GAN and make it deep convolutional, and that's something that we certainly explored as an option for generating this data, for generating this random matrix approximation. And one of the key insights that seemed to work very well was the Wasserstein GAN. So the Wasserstein GAN is a generalization of the GAN, which improves training stability due to better behaved gradients by using the Wasserstein loss function in training. Bernd gave a nice introduction to the Wasserstein distance yesterday. So that's something that worked quite well for us, as I'm going to get to in a moment. So now that I've introduced the tools that we considered, let me get to the Kähler metrics themselves. So we want to learn an ensemble of data. So in order to do so, we need to generate some data. So we need to generate this Kähler metric data that I told you about earlier. So the way we're going to do this is we're going to first construct a large ensemble of geometries and can then construct their moduli space, their metric, and try to generate a large ensemble of statistics. So we need to construct a large ensemble of Calabi-Yau threefolds, and the Calabi-Yau threefolds that we chose to look at were hypersurfaces and weak Fano torque fourfolds, which is the largest ensemble of Calabi-Yau threefolds known to date. It's supposedly bounded from above at about 10 to the 928, this ensemble of independent geometries in there. So what we did was we took about order of 1,000 Calabi-Yau geometries at fixed n with varied topologies, such as intersection numbers, Chern classes, Mori cones, etc. So we have our geometry, we have all the topological data, which is everything we need to actually construct the metrical moduli space. So now this is a function of the Kähler moduli. So in order to construct our data, we chose a single point for each geometry, a single point in the Kähler cone, which we call the apex of the stretch Kähler cone. So the parameters are these t's, and what we're going to do is minimize the volume, the sum of the volumes of the generators of holomorphic curves, but enforcing that all holomorphic curves have at least volume 1. This is known as the apex of the stretch Kähler cone. The stretch Kähler cone is this region, and this is sort of the proxy for the region of control of the effective theory. Okay, so this gives us some data. And then to be able to compare between different geometries, well, the metric is homogeneous of degree 2, so we're going to normalize by scaling such that the overall volume of the Calabi-Yau is 1. So this allows us to move from, for the experts, reflexive polytope to triangulation to Calabi-Yau to eventually to this metric of moduli space, which again is just a positive definite matrix with real numbers. Okay, so I'm about to discuss the random matrix approximations, but at first I want to just ask, okay, so we have some data. We're going to try to come up with a random matrix approximation of this data. So when do we declare success? When do we say, okay, this model is a good model? Well, there are many different ways, but a clearly non-exhaustive set of criteria is just from a human point of view, as we see visually that the features in the data are reproduced by the fake data, and we can't distinguish the fake data from the real data just by our eyes. A more precise test, which we're going to use, is that the eigenvalue distribution is reproduced. But importantly, we also want the generated fake data not to be identical to the data we put in. So we want this generated data to be a candidate for geometries we haven't yet explored, or at least be close to it. Okay, so let me start off by discussing some experiments in fixed n or fixed H11. Okay, so we have a generator and discriminator neural nets, and we have some parameter choices. And the available parameters are the actual model we take: a GAN, a Wasserstein GAN, a deep convolutional GAN, or a deep convolutional Wasserstein GAN. H11 is n, the size of the matrix. It's an MIM matrix. The number of geometries which we use for training, and a really important parameter is going to be NZ, which is the number of draws from a Gaussian at input. So remember, NZ is the number of different Gaussian draws we take to generate a random matrix. So if NZ is small, then the matrix we expect the entries will be very, very highly correlated. But if NZ is large, we expect a few correlations. This is going to be an important parameter in understanding the correlations that we see. M batch is the batch size, and critic is the number of Wasserstein GAN critic loops if applicable, and alpha is the learner rate for RMS prop. So what we're going to do is 10 epochs per experiments, and we're going to draw. I think I already mentioned this. We're going to draw our random variables from a Gaussian that could then get fed into the GAN. Okay, so what's the structure of our data? We're going to take these matrices and represent them as images, where the light spots indicate large numbers and the dark spots indicate small numbers. So we're going to take batches of 64 different geometries, and we're going to start with H1 equals 10. So we have 10 by 10 matrices. So we're going to actually put these 10 by 10 matrices in the upper left of a zero padded 16 by 16 matrix. So we're just going to take a bunch of zeros and then put our 10 by 10 matrix in the upper left. And this is going to be important for some interpolation and extrapolation experiments, which we're going to run later. And so this is the actual data. And so just by our eyes, we can see that there's, quite a few hotspots and voids. There seems to be structure along the diagonal. These are positive definite matrices after all. And this structure is presumably due to some geometric data, some topology, or this narrowing of the stretch Kähler cone that I discussed, that we can see from our eyes, and we can also see from just computing the physical observables in the string theory itself. So how can we discover the structure, and is it human interpretable? What is the mathematical structure behind it? So let's try to train. So here's some of the randomly generated data, epoch 0, completely untrained. And we're going to stick with h1 equals 10 for the moment. And we're going to take nz to be 5. This is the number of draws from the random distribution, which we're going to take to be a Gaussian. So we're going to take a few thousand of these Calabi-Yau's, h1 equals 10. And we're going to choose some subset to train on, generate the Kähler potential, so we have our data. And then we're going to test the fitness of the generated model. So one question as we go through is, can the GAN learn the features of the geometric data, but also the zero padding that's going to be important for our extrapolation experiments later? Okay, so we're going to start it totally untrained, and we're just going to click through a few different epochs of training. And we're going to see that as we go on, this is epoch 40, going to epoch 60, we're starting to learn the zero padding. We're starting to pick up some of the features that we can observe by eye in the data on the left. So this is epoch 80, and we're going to jump all the way to epoch 1000, where we learned the zero padding quite well. And at least for me, this data is pretty indistinguishable from the real data. So at least by our own eyes, it seems to learn some of the features that we needed to learn. But of course, a better way of testing whether or not the GAN is producing good data is by looking at something more quantitative, which is the spectrum of eigenvalues. So here in blue, I have the real data. This is the data we generated geometrically. In green, we have the GAN at some epoch, and then orange as sort of a null model, we have a naive Wishart model. So one can see immediately that the naive Wishart model does not reproduce the spectrum, and this is the eigenvalue spectrum on a log scale. So since I mentioned the eigenvalue spectrum, I do want to emphasize that we are not actually training on the spectrum itself. The GAN is learning the matrix distribution. So this distance here is the Washington distance, and we're going to watch as we click through some epochs how this green data distribution starts to move in the blue, and this Washington distance starts to shrink. So as we go into epoch 40, epoch 60, epoch 80, we can see this green distribution move closer and closer to the blue distribution, and the distance shrinks. And at the end of the day, the green distribution reproduces the blue distribution quite well. So this is all with the GAN. I want to mention that the reinforcement learning game with the Bergman metrics also had the same effect, but the Bergman metrics had trouble reproducing this actual peak, and it was a little more spilled out, even if we let it train for much longer. So this is one of the problems with using our human intuition to try to insert structure, that we weren't clever enough to do it with Bergman, but there's probably a better way to do it. But the GAN saw this, the GAN was able to recognize this very quickly. Okay, so we saw a converging spectra of metric eigenvalues from the beginning of training to the end. Okay, so a couple of interesting points is that the architecture really mattered. So the DCGAN clearly did the best. This is the Wasserstein distance between the eigenspectra plotted as a function of epoch, as a function of time and training. And the DCGAN clearly did the best, and the WGAN did the worst. The architecture really mattered. The other really interesting feature is the correlations that we're seeing. So remember that NZ was the number of Gaussian random draws that we took to generate the random matrix. And what we found was, so this is H1 equals 10. So it's a 10 by 10 matrix. So you might naively expect that you need 10 by 10 variables to accurately reproduce the distribution. The experts who know something about these Kähler metrics know that they generally are functions of only 10 variables. So you might expect for H1 equals 10, you'd expect NZ to be equal to 10 for it to do well. But what we found was it really didn't matter. Even if we took NZ as small as 5 for this H11 equals 10 example, the performance was quite constant and quite well for all NZ, which we think is indicating strong correlations in the data in these matrices. This is somewhat surprising, but there's a lot of structure in these geometries. So they're all connected by topological transitions. And so one might imagine that these, some of the geometric data is being preserved as we increase H11 and a lot of the structure remains. So this was so far at fixed H11. But one of our motivations is to develop a random matrix approximation that we can scale with n, because a lot of the data at larger n is much harder to obtain, and it's much harder to get a good sampling of the data at large H1. So one important question is, if we train on varying n using an appropriate tool, can we learn in a random matrix approximation that scales with n? So the idea is to use a conditional GAN that takes in n as a parameter. So we're going to do a couple of different types of experiments, interpolation and extrapolation. So the method is a conditional DCWGAN. It takes a number of moduli as an input, as a label on the data. And so we're going to ask, if we train on, so if we have data from H11 equals 20 to 30, if we train on, say, 20, 22, the smaller sizes, and 28, 30, the larger sizes, can we interpolate and learn the data in between? We also want to ask, I think more importantly, about extrapolation. If we train on smaller data, can we learn something about the larger data? Can we learn a good random matrix approximation for the larger data? So the GAN fakes data given noise, but if there's multiple classes of data, the conditional GAN, well, you pass a condition and you want it to generate certain types of data. So one example is the handwritten integer database to MNIST, which you want to be able to pass a condition and have it generate a particular number. So the question is, can we, if we train in a certain sample, can we actually extrapolate out of that sample, which is not typical of most data sets? And the long and short of it is, it actually works. And again, the question is this due to structure? So in the top plot, the middle two H21s, 24 and 26, were not trained on, and the bottom two, the upper two, are not trained on. And in both cases, we see that the as measured by the Washington distance between the log eigenspectra, the real data, and the fake data, the generative models were actually able to learn and interpolated and an extrapolated distribution that reproduced the data quite well. So we certainly see learning. It's interesting to note that the larger H11 models were more accurate than smaller H11, and we're not entirely sure why that is, but we suspect it might be due to needing to learn the zero padding. But anyways, we see learning, and the long-term goal is to be able to extrapolate to very, very large H11, which technically becomes a little more challenging because the data seems to undergo a slight phase transition and become bimodal at large H1. So there might be a little more effort that needs to put in there into the designing a model. Okay, but let me sum up. So the idea was to use machine learning to learn an approximation to the data distribution in the form of a random matrix model. And today we showed that deep generative models do a fairly good job. So the general proposal is to make approximate statistical predictions in string theory via approximate distributions, learn a random matrix approximation of the tensor couplings using machine learning. And today we saw it worked fairly well with Kähler metrics. We were able to learn a random matrix approximation of string 2b and F theory of the Lagrangian metrics. And we saw converging eigenspectra for fixed H1 and interpolation and extrapolation work quite well. We also observed a lot of structure by only needing to use fewer than H11 random draws to correctly reproduce the spectrum, which indicates correlations in the data. So more refined ideas I think might be interesting to think about for the future are to reverse engineer this for geometry. If we learn if we have a spectrum of random matrices that represent the data of the moduli space, can we reverse engineer this and ask, are there geometries that would reproduce this if we took the same sampling that I described earlier that we haven't discovered yet? I think there are many possible physics applications for having a solid RMT model at RGen, which include accident-like particles, inflation, vacuum stability, moduli stabilization, etc. All right, thanks a lot.
Great. Thanks a lot, Cody, for that nice talk. Are there any questions? All right, anyone? Just a quick question for me. Maybe I missed this. Is that this random matrix? Is it a particular ensemble of random matrices? This model, is it an orthogonal model or a unitary model that you home in?
Yeah, that's a good question. We don't know. I mean, part of it is that the data that we start with isn't easily reproduced. You can't just match a naive simple random matrix model to it, like Wishart or some convolution of Wishart and Wigner, et cetera. So, I think a really useful step in this idea would be to make it human interpretable, be able to actually open up the box and read off, what did the GAN see? Why do the distributions look like this? That was part of the motivation using the Bergman approximation, because I mean, once it tells us the values of the coefficients and the line bundles, we're done, right? We know the line bundles. We know the geometric data. We can understand it. So that's something that we haven't been able to read off from the GAN at this point, but it would be very, very useful if we could.